So, if you're anything like me, understanding the history of why things have come to bear helped me out. And I've been in this for a very, very long time. My first CAD system was Unigraphics version 10 back in like what was it, 96, 97, 97 I think it was. Yeah. That's when I learned CAD. And back then it was a completely different thing than what we have now. It's at heart the same, yes. But the interface, the GUI, the math, how things are done, etc., have changed. Back in those days, a lot of the CAD tools that we used were basically almost perfect mimics of the drafting table. Okay, what went on drafting table, what went on the real world, and to an extent they still are, but again, back then it was, basically it was a bit more rigorous and so on. So, understanding the history of NURBS, curves, surfaces, all goes hand in hand with understanding Class A surfacing and why the rules back in the day for what is considered a Class A surface were so stringent. Okay? And it has a lot to do with, obviously, math. It has a lot to do with computer graphics. It has a lot to do with the fact that, our first computer that any of us had 25 years ago, 30 years ago in our house, maybe a little bit earlier for some of us, oh wow, I had 5 megabytes of memory or RAM or whatever it was, right? They weren't very powerful, comparatively speaking, to what we have in our back pocket or front pocket or purse or whatever these days, right? So the math necessarily had to be as simple and as clean as possible. And before that, the math had to be as simple and as clean as possible. So that's why I have right in front of us this under Wikipedia, something that anybody can go get, an explanation of NURBS. And it goes into a little bit of history here and what a spline is and how they were defined and so on and so forth. So there is a lot of good information on this page. Go read it. I'm not going to get into the math. There's a lot of you guys more on the engineering side that are really good at the math stuff. And, I'll misspeak about one little thing and everyone will chase me down and, tar and feather me because I misspoke about one thing. So I'll let you go and make your own conclusions based off of what you see here in this article. It's fairly accurate from what I can tell and does a really good job describing what a control point is, what the order is, what the degree is, knots and their vectors, and so on and so forth. And, this is a linear based function, right? If this were a bunch of points that I just picked and made it let's say, 1 degree spline, right? It would just be a straight line, straight line, straight line, straight line, so on and so forth. Whereas there's a quadratic. If picking those same points, this gives me different shapes for those curves because we're changing the level, the degree of the math. You've seen me do that 1,000 times in these videos, maybe in classes and so on and so forth. Now, like I said, this is good. Get in there, read a little bit about it. I'm not going to talk too much more about it because I just don't need to. Now, I'm going to start off with a simple curve, and I've talked about this before. And yes, I'm using NX, and the reason why I am using NX and not CATIA is because this is something that I've done in NX a million years ago, had to do, and I just haven't had to do it in CATIA, so I'm sure there's a way to do it there. It's just I've never looked, and I know how to do it here. And it's an old function. You guys are going to laugh and maybe cry, and you'll see what I'm talking about. So here I have 2 lines, and I'm just going to build a studio spline. It's going to be a single segment spline, and notice I can come in here and say, all right, well, this is the degree of said spline, because I know that when I pick this endpoint, let me turn on this, pick this endpoint, I want to say G1 all the way over to this endpoint, right mouse click, and hey, where's my G1? Why can't I go G1? Well, what's going on is NX is saying even though I specified the math, I don't see those control points in there. So I'm going to go in here and delete that pole. And what I'm going to do is I'm going to draw a point over here, another point over here, and then come over here, and then this is going to be G1. Now, as soon as I do that, I satisfy the spline that I'm creating. I'm touching G0. I have my vector. You see this little arrow right over there? That's a vector indicating that the vector at this end is going in this direction, and that this curve starts out here and it's going in that direction, and the bend comes down because if I look at the opposite end here, right, I have a vector at this end, there's my vector, etc., right? You can go back and forth to see the vectors. There's your vector there, and just a line. It's just a vector. That's all it is. Now, another way to imagine this, start over again, is if I have, like, let me bring up the article again, just quickly. If I have, like how they used to define these, a flat spline, they would use things called ducts, and they eventually change them to pins and ways to hold the board, right, for shipbuilding, because this all goes back. Remember, there's water lines and bulkheads and all sorts of stuff. This all comes back from loftsmen inside of a loft, building ships. So the reason why we call Bézier curves Bézier is because a gentleman by the name of Pierre Bézier came up with the whole concept of Bézier splines and curves. You know, it's basically really smart stuff. And the way that old boats are built, and I have videos of me demonstrating a stick bending, right? You take a stick and you bend it, what happens? So that's what a NURBS curve is. It's basically a representation of bending a stick. So we have an endpoint that's held here, we have an endpoint that's held here, and we have little pins or ducts that you bend the stick on. All right, see here a little close up, to get the shape that you want. Right, we've been doing stuff like this for thousands of years. We have bows that are shaped this way. We have bits of boats that are shaped this way, instruments that are shaped this way, furniture that's shaped this way. Back in the old days when we used to use wood on cars, we would shape wood on our cars that way. You know, also anything, right? That's what we used to do. So the same concept is true in CAD, right? There's no difference. It's just the interface is different. That's it. And a lot of people have a disconnect between the real world and what happens in we'll call it the digital world. Okay, so if I have a spline and I pick this point, I want to make a spline. Let me go back in here and turn this on. And I pick that point. I just said that I want my endpoint of my spline to go right to that point. And then if I come over here, I'm not going to change the math or anything. We turn that off. And I come over here and say, well, there's my spline. It's basically 2 points, right? Talked about this in other videos recently. Now, if I come in after I've created it and I start cranking up control points, so what's happening is between the end point, which is my anchor, and this middle control vertice, this acts as the vector direction. That's all this is. It's the vector. And if I come in here now, right mouse click on this and say infer G1, what it does is it takes this vector and aligns it to the end, the vector that's formed at the end of whatever curve I use. If this could be a circle, another spline, whatever. It has a point and it's got a vector direction on that point. So that's all this is doing. I do the same thing at this end for G1. And now I can't move that off of the vector, and I'm adjusting the shape of the curve. And if I do not apply what's weight or tension or anything like that, so if I click on this, notice I have the ability to move the location of that point. Okay? And with that, right, still maintaining the vector. G0 is broken, G1 is there, but I'll just go back to G1. Now, I can manipulate the shape of the curve, and that's that. Now, there's another thing that you can do with these curves, right? In the old days, you used to be able to apply weights at these, and you could pull in that shape a little bit and, adjust things at those points. That math still exists someplace in there, right? If you want to adjust the tension, now you just grab this and you move this around, and basically I'm adjusting, in essence, the tension at that end, even though it's not the tension. It's kind of like the tension, right? I'm just changing the shape of the curve. But if I employ a tension or something like that, what I'm doing is, again, in essence, is applying what's called a weight. And basically a weight would be, having call it a gravitational pull or whatever. So if like I said, Alias is really good at doing stuff like this, where you can pick a point and then say, oh, I want to weight the curve, and what it'll do is it'll bring that curve in a little bit and do stuff like that. Okay? So there's all sorts of things that you can do, but I'm talking about base math, right? I'm talking about the location of the control point without adjusting any tensions or anything like that underlying math to said point. Eventually it'll be a surface, okay? So this, basically what I'm doing is imagine I'm stringing a piece of wood, right? It's got tension. I'm fixing it here, I'm fixing it here, I'm forcing it tangent, forcing it tangent, and then the wood bends. Imagine perfect grains, perfect, we're in computer world, so theoretically everything is perfect, and that's what we see here. Now, those control points can also guide a mill. All right, I can take these 4 points, point 1, 2, 3, 4, just those 4 points. I can extract just those 4 points. If you saw me right now, I'd be holding up 4 fingers. You'd see me holding up just those 4 points. That's it, nothing else. 4 points, 1, 2, 3, 4. I can take those 4 points, put them in a very small text file, right? Because text files are very small, right? They're, minuscule. Those 4 points, and I can take those exact 4 points and go to other CAD systems that use NURBS and plot this exact curve with 100% accuracy, because math is math. Now, I could take those 4 points, stick them in an NC, something that's numerically controlled, CNC, numerically controlled mill, and plot this curve without actually having to represent that curve. Math. Okay, so that's why control points are really important. Or in the old days with fancy cars and things of that nature, you used to use French curves. What's a French curve? Basically a giant shape that was a conic. Different portions, very long, stretched out conics, maybe something flat, maybe with a great peak, shoulder, so on and so forth. Same thing, airplanes were defined that in said fashion. Why? For lots of reasons. Why conics don't inflect, right? They can't invert. I could technically take out one of these control points, have a conic in between here, have a control point in its one perfect position to match the vector and match the vector. And again, those 3 points with a row value, right? The row value of the conic is an ellipse. Is it a parabola? Is it a hyperbola? And you can define that curve with very simple math. Really super easy. And things look really, really good. For years, all I've heard is you got to use super advanced curves for all these crazy shapes and blah, 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 blah. I've used conics, little, third order, 2-degree curves on exterior panels for primary surfaces, for lots and lots and lots of things over the years. I didn't have to accelerate the edges. I didn't have to do this. I didn't have to do that. Because you don't have to, right? The blending can take care of all that for you. And people say, no, it doesn't work that way. Yeah, it does work that way, right? It's just people want to get fanciful with their methods and techniques, and whatever works for you, great, works for you. I don't care. But I'm telling you what I've done and what's worked for me. And I've done a lot of things over the years. Now, The reason why I'm using NX to demonstrate this, very long-winded video, is I'm going to go over here. And what I've done is I've made a surface. I X-formed it, right? 3 degree by 3 degree, single patch, and I extracted the points. And I'm going to go ahead and hide that X-form. So those are the points that make that surface. Now, I should say control points that make that surface. Again, I could take these control points, send them off to a machine, somebody that knows how to program an app, somebody that has the old ways, right? And I can cut that surface with 100% accuracy with whatever tolerances the machine has. Obviously, you know, if it's a cold day, hot day, right, cutter, blah, 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 you know, let's not get too pedantic because somebody will get pedantic. And in theory, I can take these points and put them in any CAD system that'll generate a surface from those points as control points and get the exact same surface 100% of the time, every single time, no matter what. And, you know, again, a tiny little text file with these locations in those very old computers 1,000 years ago, I know, it's like 50, 60 years ago, made all the difference in the world. I could not represent that surface. I couldn't shade it. I couldn't, and you know, the old original stuff couldn't do that. So I would have to have these points. So surface to surface, you know, joints, blends needed to be necessarily as simple as possible. And of course, that also affects everything downstream. You know, I remember the old days when I first got into the unigraphics and old CATIA. Doing a simple offset surface took time because there's a lot of math involved in an offset surface, okay? It's just the nature of it. Now it happens in a blink, you know, unless it's a super complex shape, you're doing some weird things, then it may take a minute. But, you know, computing power has kind of gotten a little better. We have hard drives that can, you know, store the entire Library of Congress on my laptop. You know, I have all that at my fingertips. So what we have here is a bit of history on why things happen the way they happen. Now, part of the reason why I'm using NX for this demo is because there is a function called from poles. And this tool is old. Okay, this goes back probably to, I would say, the start of NX, or when they introduced a GUI like this into the system. This goes way, way, way back. It's never been updated because it's not really necessary to update it anymore, right? They may choose to change their minds eventually. There are still some places that will plot out a surface using control points. You know, those mirrors that they use in satellites that need to detect something very, very, very far away and need to be really super precise, right? They'll still make sure that those surfaces, there's only one way to make those surfaces perfect. Well, back in the day, I should say. But now, you know, there's different ways. And plotting those surfaces out mathematically out to the, you know, Brazilianth decimal place for the point location allowed you to make super accurate surfaces. Again, for lenses, reflectors in these satellites that are measuring things billions and billions of miles away, trillions of miles away in some cases now. So what I want to do now, because this is an old tool, it's called from poles. You'll notice I extracted the point set to get my control points. It's the easiest way to represent what I want to represent, show you. And I'm not going to do multiple, I'm going to do single. I'm going to do a single patch to really simplify it. Notice everything goes away because if it's a single, we're going into we'll overly simplify it and make a bold statement that someone's probably going to spurg out at. Oh, it's not Bézier. It's in essence making a Bézier surface. Okay? In essence is what it's doing. And I can import those points from a file, but in this case, I'm going to select OK. Remember, this is an old menu, so it has absolutely zero intuitiveness. So read your prompts, your status and queue line. I'm going to select OK. Now, it's going to ask me for the points. What points do I want? So in this case, the direction will change the UV direction of the surface. But I will get the exact same surface. Now, I'm going to start out here. I'm going to make sure I have existing point set. I want point 1, 2, 3, 4. I'm going to select OK because I'm done picking my points. Done specifying points. It's asking me way in the bottom. Yes, I am. Now notice it comes right back to the point selection menu because I need at least 2 separate rows. I'm going to go 1, 2, 3, 4. You know, those kind of look like control hulls, control points, control hulls. Kind of neat, huh? I'm done picking, select OK. Done specifying points, yes. Are all points specified? No. I need to specify another row. And once again, 1, 2, 3, 4. Whoops. Okay. Done specifying points. Yes. Specify another row. 1, 2, 3, 4. I'm done. Yes, I am done. Specify another row. All points specified. Now watch what magically happens as soon as I hit that. I get a surface. Okay, there's my body. Notice there's no history there. Before I refresh the screen, I'm going to show my X-form. And take a look at those control points. Take a look at those hulls. Take a look at that. Okay, zebra striping on the surface. It's fading in and out. And we have, for all intents and purposes, an identical surface to the original that was drawn. So I'm just going to refresh to clean that up. Let me go ahead and hide the points. Let me just turn that off. And what I'm going to do to prove it is I'm going to go into analysis. I'm going to go to deviation gauge. There's my X-form, reference this body, min, max, inner tolerance. I just want say analysis object, we'll say user defined. And now mind you, this is in metric, right? This is a metric file. I do not see a single anything outside of perfection on that surface. So again, if I sent those points, those control points for that surface to be machined, I will, in essence, be programming perfectly every single time to the exact surface that I need. Because those control points drive the shape. Those control points make that surface. And I can translate those points from one CAD system to a next. I can write them down manually and enter them in manually. I could do whatever I want to, and as long as the CAD system or the CNC system is NURBS based and does things with standard NURBS modeling math, which most of them do, you will always 100% end up with the identical surface, always. Okay, never say always, always, never say ever, blah, blah, blah. In this case, always. Because the control point, math is math. It'll never be anything different, ever. And this is how things used to be done back in the old days, right? Before you could just say, hey, I'm going to touch the cutter here, and I'm just going to run along that surface. We didn't have that. You had the control points. So it was necessary to keep the surfaces very simple. Again, for lots of reasons. Not just that, but that's one of them. Again, I could take those points, send them to whoever, wherever around the world in a very small file, Or I could write them out and mail the package to somebody and they could open it up, the old drawings with the XYZ coordinates and so on and so forth, because that's how they used to do things. And I could manually program that into a computer with the right cutter, with the right this, then blah, 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 CNC, and get that surface. The only tolerances that you would have, no modeling tolerances, no this, no that, only tolerances you would have are the manufacturing tolerances that are affecting that surface. That's it. No CAD tolerances, no translation tolerances, no nothing ever. And that's why surfaces and the way we do things, Class A, in the olden days, was critical to keep them as simple as possible. Now our computers are super powerful. We can do more. We have more exaggerated shapes on our vehicles, on our airplanes, on our products at home, right? I look around and detergent bottles, things I've worked on. Just even something as simple as that has some pretty crazy drastic shapes on it. And that allows us to do more. So yes, there is the absolute strict definition of what a Class A surface is. And the reason why that absolute strict definition is that way mathematically is because of necessity, because of what we had to deal with back in the day, how we had to make things. And I would say, to an extent, excuse me, those parameters have opened up a little bit because of computing power, because of what we can do. Okay, these tools are now remarkable. What you can do with one of these CAD tools, whether it's CATIA, NX, Alias, we have ISOM inside of CATIA, ISOM Surf, Classic, Rhino, even other ones. They are astounding at what they can do. And that's part of the reason why the history says this is what the surfaces needed to be. But now, because of technology, because of what we have, some of those mathematical rules, I still, use single patch for primaries. I still use, as simple a surface as I can in a lot of cases. But there are times when I let that float because I'm using a circular and NX, right? I've got a section surface, circle or conic or whatever, and it creates more control points than is allowed by math. And, the Class A experts out there that tell you that you're a silly person. But you know what? I got a parametrically driven model that allows me to do what I want to cleanly. Go for it. All right. Again, some people are going to spurg out about it. I don't care. Just make awesome things, please.